Okay. Can I start? Or?
Yes, please go ahead.
Okay. So this is the third and last presentation for the JEC section. And in particular, as Enrico already mentioned it here, one of the topics on which we are also focusing is modeling the perception of quality of an individual subject with a neural network. And once we train such a neural network, we call it an artificial intelligence-based observer, or AI observer. And we train this neural network in a way that when they receive an image in input, they predict a 5-class probability distribution, mimicking, the scoring behavior of a subject on the 5-point ACR scale. The long-term goal of this research here is to design a multimedia processing system that account for individual preference when encoding the content. Now, what are the research challenges here? Obviously, already training a model for most prediction involve some of the challenge, but these challenges are somewhat amplified by the question of modeling individual perception of quality. And two are those, we have two main challenges here. The first one is that individual opinion score are typically noisy, and learning from noisy opinion score is really demanding in terms of complexity of the architecture, as well as a number of training samples that are required to get a stable model. On the other hand side, we have the typical issue of having limited data sets, especially in the case of modeling individual perception, where it's very difficult to have the same person rating a higher number of stimuli. So one way to mitigate these issues here is to work with shallow neural networks, for instance, okay? Or you do transfer learning, or also data augmentation. I mean, we will somewhat navigate over our ideas to deal with these challenges here and the related results. Now, our first idea was using shallow neural network, and what the idea is that of taking an input signal, extracting a handcrafted feature, and then mapping this handcrafted feature to the quality scale. Now, what we observe as experimentally is that if you want to use a shallow neural network, typically for modeling an observer, it's enough generally to use 1 to 3 hidden layers, and on each layer here using like around 5 neurons. I mean, this is an empirical observation based on our previous experiments on the thing. And the number of hidden layers here might give you, for instance, information on the complexity of the subject that we are modeling. It's a very simple approach, but yet with this, we already have, we can already have some results in terms of mimicking. In fact, what we realize is that if you take your AI observer and use them on a large scale data set without subjective annotation, we are talking about 20,000 PVSs, let's say. We use the AI observer to rate all these PVSs that come from 10 different sources, and then report the quality estimated by the AI observer versus the inconsistency of the AI observer. Remember, the network output a probability distribution, or we can take the variance of that probability distribution as a measure of inconsistency. And you see that for all the sources and for all the stimulus, basically, the AI observer is mimicking the lower inconsistency of the subject at the sum of the quality scale. But the network is not trained for that. It's something that the network is mimicking, because you train the network to predict the opinion score, but then it is able to replicate the higher accuracy of the higher accuracy of real observer as the sum of the quality scale. So this is one aspect that shallow neural network could mimic. And this comes from a work that we published at ACM on ACM-Tom. Now, the problem with handcrafted features is that they approximate the input signal. You take the input signal, you need to compute features. And the overall accuracy of your system strongly depends on the accuracy of these features to represent your signal. And also, if you use handcrafted feature, you are no more really mimicking the process of that the real observer follows. The real observer see the wall signal. You might want an architecture that allow you to input the signal that the observer see. On the other hand side, there is this issue of overgeneralization that handcrafted feature suffers. What we mean here by overgeneralization is that different subjects might perceive the same features differently. Like think about somebody that is just very sensitive to the blur on edges, and some other ones that is sensitive to the blur at any part of the image, like texture, edges, But in general, handcrafted features that you find available, typically they focus like on a specific idea, like trying to assess the blur that will be caused maybe by a Gaussian filter or any other specific filter that you can use to generate blur. So the idea will be what can we do to really mimic the whole process that the subject follow, like inputting the signal that we show to the subject during a subjective test. And the answer is deep neural networks architecture that takes as input the whole architecture and try to build the feature that really characterize the person that we want to model. And in particular, we have been investigating the effectiveness of two-band architecture, deep convolutional neural network, as well as recently we are also working with vision transformers. Now, the problem with deep neural network is that they are highly demanding in terms of data, but we don't have this data. So we talked about an approach that combines maybe transfer learning, data augmentation together to try to train the AI observer of a subject. Now, this approach, we call it a human in the loop training process of the DNN-based AI observer of a subject. It implements five steps. The first step consists in training an AI observer with several deep convolutional layers. It could, or in general, several deep layers and then how do we train this first AI, this network? The idea is to synthetically annotate a large-scale dataset. By synthetically annotation here, I mean an annotation here done with an algorithm. It could just be different level of compression that you level with different, with different numbers, or use an objective metric to label your data and so on. So you just need to train a network that learn at a high level what means assessment of quality assessment. Then at the second step of the iteration, you invite the subject that you want to model into a subjective test where you show him a certain number of stimuli to evaluate. The subject rate those stimuli. You use the data that you collected from the subject to pursue the training of the network that you pre-train at step one. Then use the network that you obtain to make inference on a large-scale data set, obviously without subjective annotation. What is the goal of that inference? The inference that you make is to figure out new images for which the network, the AI observer, is predicting quality with high uncertainty. So we take the AI observer, we use it to predict the quality of several images. The AI observer output the probability distribution. We select the images for which the AI observer is making prediction with high variance. That means that the AI observer is uncertain about the quality. We took this image, we take a quantity of these images and turn back to step two, show these images again to the AI, some of these images to the guy again. The guy rate them and we repeat the process. Anytime we move from step 5 to step 2, okay, it's a loop. And for the moment, we are just stopping based on the availability of subjects. We don't have any convergence criteria so far. And the model that we get after the last iteration is the AI observer of the subject. Now, let me show you some results that we obtained by putting 5 subjects into the loop and making 3 iterations of the human in the loop training procedure. The first table is what we are going to use as benchmark. So we basically ask the 5 subjects to rate twice the same images, and we are using the repetition performance as a measure of a subject to predict himself. We want to understand whether, the AI observer is having a performance that approaches the ability of a real subject to repeat himself, for instance. And in the second table, instead, we use each AI observer to predict not only the corresponding observer, but also other observers. If you focus on the diagonal of the second table, you will see that in general, let me say, no, the AI observer number 1 predict his observer with an accuracy of 63%, while the observer himself, repeat his first opinion score with an accuracy of 56%. The idea here is not to say that the AI observer is better than the observer. It's just to say, are we having this, the number that we observe with the AI observer, are they comparable to the ability, for instance, of the subject to repeat his first opinion, for instance? And the result was that, yeah, the number are comparable. And something that is also interesting, if you see that the diagonal, it's mainly highlighted here in bold, is because it was important for us that the AI observer of each subject predict that subject better than any other subject. This was in order to somewhat tell you that the network learned something about the subject that it is mimicking, and not just some general features that are valid for any other subjects. This doesn't happen only for one subject, observer number 4, for which there was an issue in the subjective test. And if you are interested, you can see that you can have a look at our QMX 2023 paper on the topic. And yeah, so this result, instead we obtain it by putting 19 by using applying our looping process to 19 observer, but unfortunately only 1 iteration. And then we took the 19 AI observers and give them as input 3 images that come from the same source, compressed at different level. The first image is the most compressed one, and the last is the less compressed one. And plot here the distribution of the opinion score obtained by the AI observer. And it is interesting to see that the distribution of opinion score that you see here, it's more or less what you would expect in a real subjective test. Basically, you are, again, this is a proof that we have different networks, and each of them is more or less mimicking what you might expect from one subject in the context of a subjective test. It's again a result taken from one of our papers that we published on signal processing and image communication. And some other thing that we wanted to really check whether neural network can mimic. We are talking about mimicking, not we are interested in aspect that you don't train the network on purpose to do, but at the end you realize that in your prediction of quality, maybe they have that characteristic that you have from the subjects. And in particular, we are saying, if we generate the subjects in a way that we know the bias and the inconsistency, train the neural network for each of these subjects, then test the neural network of each subject. Will the neural network of the subject preserve the characteristics that the simulated subject, that the original subject had? And in particular, we use the model behind Sorial to simulate opinion score in a way that we knew exactly what was the bias and inconsistency of each subject. We simulated the opinion score on 1,000 images for which we knew, for instance, the most in that case was used as grant of quality. And we can discuss maybe offline the detail on behind this simulation, but the result here is that in terms of bias, the bias of the AI, when we test the AI observer on a test set, right? Not on the, we take a test set, different images, run the AI observer, and you estimate the bias as well as the inconsistency of the AI observer, and do the correlation with respect to the grant of bias that we use for simulation and the grant of inconsistency, there is very high correlation between the characteristics of the AI observer to those of the simulated subject. I mean, for the bias, you might say that it's quite simple. The network just learned that we have high opinion score. But keep in mind that in the simulation, there is the inconsistency. So you might even give high opinion score, but the inconsistency might somewhat trick the network. But the network got that. And for what concerns inconsistency, there was kind of dispersion in general. We still still not able to explain why there is this dispersion. But the fact already that there is correlation between the inconsistency of the network and the inconsistency of the subject, it's quite interesting, because for many learning tasks, the confidence of the model does not correspond to the confidence of the human in doing the same task. But this happened for the task of quality assessment. Yeah. Now, to summarize, to complete, we have a number of open research questions here, and in particular, we're asking ourselves, is our procedure convergent, and how can we assess the convergence? The other question is, that procedure that seems to work well for us so far. Do you think more or less that we can suggest it as a standard way to do test for the training of AI observer? And in particular, we believe it has two features. Like, it somewhat, avoid the collection of users data, because you just ask the opinion score on the image, on the images on which the network is confused. And then you also mitigate subject fatigue, because you don't ask everything at the same time. The other question that we are addressing is, what is best between deep CNN and vision transformer? By the way, the result I show you so far, the result for this result here, when we compare a deep neural network, a deep CNN and transformers, we get comparable results. And yeah, now very important. At this moment, we are collecting an opinion score to train the AI observers of different persons and so on. And we will be super happy if some of you interested in joining our human in the loop learning process. And just time by time, we will ask him to rate, using an online tool, a number of stimuli that will be used to train his AI observer. So thank you for your attention, and looking forward to answer your questions.
Thank you, Rick. Okay, Ali, please.
Hello again. Thank you for the presentation. I have two questions. One might be very short. I'll start with that one. At the slide 9, you are showing some images with some histograms next to them. Why do I expect? Well, okay, for the bad one, let's say we don't expect much of a deviation in terms of in the distribution. But why do I expect wide distribution on the, let's say, around the good and fair quality level, while very, I would say, certain opinion of the whole population when it is compressed a little bit more for the same content? Is this something that we also observe in many of the JPEG compression datasets?
I mean, at least from my personal point of view, this distribution of opinion score, these distributions of opinion score here looks realistic. I cannot really give a strong opinion regarding the general behavior of the distributions in front of the same source compressed with different level of JPEG compression. But if you ask me to give a subjective on the evaluation of this situation, I will tell you that it's look realistic. I don't know if any other in the audience is more expert on this, on how and on the expected diversity among user opinion on the same source compressed at different level of JPEG compression. Not sure whether my personal sensation regarding the topic is helpful, but Ali,
no, thank you. I was thinking more or less. Well, what I was expecting is actually having a similar behavior. So I just wanted to open a discussion and hear your opinion. But that's that's good enough for me actually. So we can move on to the next one. Thanks. And the next one is, what is the benefit of training a deep neural network and then predicting my behavior as a subject, rather than, since you have my data as a subject here already, because you want to train with my data a neural network, you can learn my bias and inconsistency and so on, the other variables that you were also introducing in your previous presentations today. Then you can model my behavior and then randomly generate my votes according to that, or apply these to a baseline prediction at my behavior.
But then you are, if you, what you are saying there is work if you assume that all those parameters that we have are totally capture your behavior. So what I'm saying, so, but it's we clearly, if you agree with me that all these models are oversimplification of the true system, of the whole system, it's clear that then if we do as you are suggesting, then we are oversimplifying the behavior of the subject. That's why we are using something that is more complex than like a deep neural network to hopefully capture all those aspects, but some other stuff that are not trivial.
Okay, and I get the wrong impression when you compare the predictions by the neural network to the serial model generated subject. Maybe, but then what can be done for evaluation is more interesting, maybe to me at least, would be trying to capture this behavior with the serial model or ZRAC or your models that you presented earlier, then try to generate a observer based on these behaviors, and then compare the performance to the deep models that you.
And I totally agree with you. And also maybe there is my fault also, in the sense that these simulations here are meant to illustrate what the network can see. I mean, what the network can simulate that we already know. Like what the network can mimic among the things that we already know, like bias and inconsistency. What are those that the network can simulate? But the other things we don't know, it's exactly what we were discussing before, right? We don't know other aspects of the human behavior. And the research, the main scope of the research is in fact to understand if the network is simulating other aspects that we unconsciously use when we are scoring the quality. So it's indeed one of the open research question of our, in our stream.
Okay, thank you very much.
By the way, thank you for your suggestion on how to, we will definitely take into account your suggestion on how to better assess the performance also in the future. Yeah.
Okay, thanks. Any other questions? Otherwise, we can close the hybrid session here. Thank you for your patience and thank you for attending. So I leave the floor to the chairs.
Okay, thank you, Enrico and Lohik, for very nice session and presentations. Let's move on then with the AVHD session. Who is going to run that? Is that Margaret?
Well, I don't think we discussed who would run it. I put a variety of different papers that fit well there. Let me take a look. The first one is Ali Nance.
And just to that point, you didn't fill in whether you are okay with it's going to be recorded or not?
For me personally, it's okay.
Okay, well, I will write a yes there in the presentation. list.
Yeah, Matthias speaking. For me, it's medium because I'm presenting some stuff which will be presented later and is also not fully ready because I just want to give a glimpse. So maybe if it would be okay for you, I would prefer not to have that recorded.
Okay, which is this the next presentation or
19?
219.
Okay, I will turn turn the recording off at that time.
Okay, thank you so much.
Did you fill in the list of the presentation?
I just added it for Matthias. And
Okay, right.
Syed, you're right after Ali. And could you also say whether we can record or not?
Hello, is that me? Hello.
Yes.
Yeah, okay, it's fine. It's fine. You know, it's been recorded. It's okay to me.
Okay, thank you.
Yeah, thanks. Thank you.
So with that, Ali, go ahead and begin.
All right, thank you. Hello. Today we'll talk about acceptance and annoyance of video quality in the context of online social media platforms. It's a collaborative work between my colleagues from Meta and me and Patrick from Nantes University. I will first start by introducing acceptance and annoyance. I think in the last VQEG meeting, if you were there also, we had another quick discussions with the preliminary work about the acceptance and annoyance that we did. But for those who were not there, I'll introduce quite briefly. So the acceptance and annoyance paradigm defined as a broader term than video quality to define the quality of experience. It takes into account the user expectations because user expectations has a major impact on user satisfaction. And we use the acceptance and annoyance paradigms to measure the user satisfaction for video streaming services or online social media platforms. Previously, what we did and I presented in VQEG, last VQEG meeting, was a preliminary work on this regard that measures the remaining data, battery, signal strength, and so on, different contexts on the expectations of video quality in terms of for the users. And prior to that, Jing and Lukasz and other colleagues conducted another study where they assess the impact of basic versus premium subscription and also viewing on a TV or versus on a tablet, and what would the impact on these conditions on the user's expectations, hence the user satisfaction. You can find the links to those here. I'll send also I will share some of the results of this study and compare it with these studies in the future slides. So how we measure acceptance and annoyance is quite similar to absolute category rating experiment. Traditionally, it was a multi-step experiment. So first we were asking, is the video is acceptable? And then you either reply with yes or no. And if the video is acceptable, we take it one step further. And is the video annoying or not? We measure that. If the video satisfies the user's expectations completely, we say that video is also not annoying, so we get the highest score. And we represent this numerically by 3. And the worst quality would be here numerically by represented by 1 and not acceptable. And acceptable about annoying will be the middle ground where the video is still okay, but not fully satisfies my expectations. And in the work that I just mentioned from Jing and Lukasz and Patrick, in that work, also a single-step version of this approach was introduced, and it was actually shown that the scores that are acquired in this single-step approach was statistically insignificantly different than the one that is acquired in multi-step approach. So because of its simpler representations from those days forward, we used the single-step approach to measure this. And in this study, we did a series of experiments where we first measure the acceptance annoyance, and then also we measure the video quality on a standard 5-scale rating. We conducted the experiment in the lab with an iPhone 14 Pro, and all the content is user-generated content. They are vertical, 1080p, 5 seconds long, no audio with varying FPS. And they are all encoded with H.264. And we use the 6 PBS generated from all the SRCs. So we have a bit more than 300 PBS on this data set, 300 content. After we get the results, we actually represent the video quality from 1 to 5, 1 being bad and 5 being excellent, and the acceptance annoyance MOS as the not acceptable to not annoying from 1 to 3. But we also use the more of a categorical representation where we use the Fisher's exact test to determine the category of acceptance and annoyance for each video. This is the visual representations of the algorithm that we use. So we have 5 categories. The 3 main categories are where we voted, but depending on the distributions, we can place them into an unsure threshold category, kind of. And the mean of these categories were used in the previous studies as the threshold for annoyance and threshold for acceptance. And we'll do the same in the following slides. So when we do that to the 336 videos, I assume, that we have, here is a rain cloud plot, and the color codes will be the same for the rest of the plots. So this is the not annoying category, annoying but acceptable category, and not acceptable category, and they are plotted against the ACR MOS from 1 to 5. So here, what we have is also the unsure about annoying and unsure about acceptance categories. We check the mean of these categories. They are here on the box plots. And we see that actually, if we ignore these, let's say, threshold categories, we see that there is a clear distinction in terms of MOS values between the 3 main categories. So this is good to see, and also it means that we can actually pretty much use a simple mapping function from one to another without much of an error. And we find a mapping function that fits to that, which might be useful to many applications, to be honest. So I'll leave it here for you to benefit from. But also the other thing here is the performance of the metrics that we use to assess the category acceptance and annoyance categories. So we evaluated a short selection of metrics, let's say. Some of them are here very obvious. You can see that the ACR MOS is not exactly an objective quality metric, but rather this is here included here to put a theoretical ceiling that is like which values can be actually achieved by if you have the information of the mean opinion score values. And then we use the VMAF and UVQ to sometimes exchange the values that we have, granted values, and sometimes fully rely on the objective quality metrics at the 3rd category. So let's start with the first one. We can see that here we make an attempt of taking the source value, MOS value of the source content and multiplying it with DMOS to get to estimate the ACAN MOS and ACR MOS values. And the Spearman correlation coefficients between the two are quite high, I would say. And then we try to model here, replace here VMAF, ACR DMOS with VMAF, and also UVQ with ACR MOS for the source content. And we see that we see a reasonable drop in the performance, not much for VMAF, but quite a bit for UVQ, which is well, expected, as you might imagine, from the superior performance of VMAP and also a more challenging task of predicting the source content visual quality by UVQ. And also fully when fully trying to estimate the quality with VMAP or UVQ, we see that VMAP is actually quite correlated with the DMOS values. Not as much with the acceptance annoyance MOS, which is also, again, expected because that takes the source content quality into account. But when we combine both, we get a reasonable Spearman correlation between the predictions and the ground truth acceptance annoyance MOS. We can also look at this not in a continuous way, but more of receiving operating characteristics analysis. And we can actually put these as AUC values into a table. Again, the same table, and we see that, well, more or less the relative performance of the metrics holds true. So let's dive in a little bit onto the predictions. So as you remember, VMAP actually performed really bad in terms of Spearman correlation, also AUC values to predict the acceptance annoyance categories. Now we visualize it actually here. So this is on the x-axis, on the horizontal axis, we have VMAP score instead of the ACR MOS that we had in the previous slides and the same categories. And we see that we have very high VMAP scores sometimes, even for not acceptable category content, which is acceptable because VMAP is not a measure of mean opinion score rather as DMOS. So we have these kind of cases all the time. But what happens if we use the mean of these threshold categories, mean values of these threshold categories as the threshold to predict the acceptance annoyance category of the content? So crosses here is exactly the same distribution. Crosses here represent misclassifications, and these vertical dashed lines are the threshold values for annoyance and for acceptance. So as you can see, we have quite a bit of misclassification with VMAP. So VMAP alone, as expected, not good enough for user-generated content, especially to predict acceptance annoyance. What happens with UVQ is UVQ is slightly better, but it uses a much shorter range in our dataset. But I believe that has to do with UVQ rather than the dataset. That's a pattern that we observed in the past too. But someone else with more experience, maybe on UVQ, can confirm. But I think this holds true for other datasets too. What happens is we have again a bunch of misclassification, as we also see the numbers of in the SORCC or AUC values before. So what we did next was combining the SRC MOS, normalized SRC MOS, ACAN MOS of the source content, then multiplied by VMAP with VMAP, and again normalized, so that we are operating in the 0-1 range. And now we see that we have almost, I would say almost close to perfect prediction. We have some errors, but they're not super far from the threshold. And actually, we don't have extreme prediction inaccuracies on non-acceptable categories that as we see in the VMAP. And then similarly, we can also replace the term for the source content quality with the UVQ, and again normalize it. And what we see again is, well, slightly higher number of misclassifications and a bit concerning ones like this, where we say not annoying to the not acceptable content, which is not really desirable in practical applications. So despite all these, I would say that if we have access to a metric that reliably enough predicts the source content quality, I think we are close to reliably use these sort of models to predict the acceptance annoyance categories with slight misclassifications here and there, but I would be okay with those. And also, based on these metrics, we can again put some threshold numbers to play. if you want to check, compare the VMAP, especially in this case, with the previous studies, I put also VMAP values here, where we have the acceptance and annoyance thresholds corresponding to 34 to 68 here. In this context here, where we had the basic versus premium subscription and TV versus tablet viewing, we have quite different numbers acquired. This shows the impact of the context, and also this is showing the impact of the source content quality. In the previous study, I would say it's more designed towards video streaming service experiences where the source content quality is rather high. But in our case, we had low quality source content, maybe not equally represented, but included in the data set. So this reflects the results we got is actually quite in line with what we expected, and we happily put some numbers on it, and we can highlight the importance of a reliable metric to predict the source content quality or source content acceptance annoyance in this regard. So then maybe we can even improve this more, I would say, more significantly. Yeah, there is a which I already summarized, but yeah, there is a larger room for improvement in predicting the source content quality. But VMAP is reliable enough to use for the rest of the quality, to estimate the quality loss that is occurred during compression. And in the next step, or also the current step for now, is to collect another data set that uses more modern compression algorithms, such as AV1 actually, and also the HDR content. So we are working on developing and designing this experiment at this moment. That is all on my side. If you have any questions, I can take them. Yes, Lucas.
Hello again. Thank you so much. I think I'm on a track to record number of questions in a day, so let's keep it that way. First of all, I really love the rain cloud plots, or whatever you call them. That's really informative, I would say. My question is, you used vertical videos, right? Did you do something special to use VMAP on those, or did you just use the 1080p model and out of the box?
Yeah, it's the 1080p model, 1080p negative model, I would say, I think.
Oh, it's VMAP NEG.
Yeah, I think so, yes. I checked both. I think they're more or less the same, yes.
Yeah, and you did not flip the videos or anything like that?
No, not at all, no.
Okay, thank you.
Okay.
Nabajit, go ahead.
Yeah, hi. Thank you again. Same like Lucas' comment, very nice plots. I also loved it. I just have a question about the encoding settings. Is there a particular reason why you are choosing different CRF values here for each resolution?
That was just designed to mimic a general behavior on video coding parameters of social media platforms. Nothing specific here. No.
Okay, and my second question is, how do you define annoyance? Annoying, but the annoying part? So
I think maybe I can actually, I meant to include that in the slides as an additional slide, but I forgot. So I will just show it on my screen, what we have inserted to observers. Well, of course, we use the translation of this, but, because the experiment was done in France, and people who did the experiment were speaking French. So we use the translation of number 2 of this. Sorry. Yeah, of this text. So the video is not annoying when its quality satisfies or exceeds your expectations. The video is annoying but acceptable when its quality is acceptable but not completely satisfies your expectations. And the video is not acceptable when its quality does not meet your expectations. Such video quality makes you think about skipping to the next video. This is the exact instructions we shared with the participants prior to the experiment. And this is how we define not annoying.
Sorry, just to understand, this was done in French, right? So the actual.
That is true, yes. Yes.
Okay, okay.
We also had some text overlays and stickers on the videos, some of the videos. 1/3 of the videos include those stickers and text overlays that is typical to user-generated content, and they were also mostly in French or in English, but understandable by a French person. With common words between English and French.
Okay, okay, thank you.
Welcome.
Okay, are there any other questions? I don't see any. I would also like to say I'm really impressed by how you presented your data. That was very effective, those plots.
Thank you.
Okay, so thank you. And let's move on to our next presentation, which is Saad Uden from the AGH University of Krakow.
Hello. Hello all. I'm sharing my screen. Yeah. Is it fine now?
Yes.
Hello. Yeah, okay.
It's not in the presentation mode if you wanted to have that.
Is it fine now?
No, no. Thank you.
Okay. Hello all. My name is Said and I'm associated with AGH UST in Krakow. It is a short presentation which I recently presented in September at a conference, in local conference at Poland. The topic of presentation is quantization parameters, which is based on video quality system and MPEG codecs. And we basically I found trade-off between those codecs and their regarding VMAP values. So as all we are aware that the video streaming application, it's is a continual growth, and the demand is the growth is going very high, and it is projected that it in few years, a 10 years of time frame, the video centric application will be in a higher demand. Basically, the users they demand very high resolution content, like in full high definition mode, even in ultra high definition mode. We have 4K now, 8K content in future development, and as these resolution demands a high processing power and a very huge storage. Now the issue of tackling up that processing power and storage, we use video compression. And the video compression is basically there is a lot of codecs embedded or coming up with a lot of vendors, and that is embedded with a lot of technologies operating with streaming application as well. And those suite they are basically providing that part of coding and encoding and decoding procedure. You can see here each codec, it come up with the suite of parameters, like you can see the versions, the QP ranges, which like the suitable or optimal ranges, and there are kind of encoding parameter. For example, if you want to set like VBV mode or constant bitrate mode or variable encoding mode, so we can set up, and it is operable with specifically those codecs. Generally, we have a few bitrate rate control modes. Number one, it is CBR, constant bitrate, average bitrate, and constant encoding. In constant bitrate, basically we limit the encoding process and encoder. We inputted the specific bitrate to that encoding to be operable in for the video streaming. That is CBR mode, and it doesn't exceed with that limit. In average bitrate, we just give average bitrate like 4 Mbps or 5 Mbps, 6 Mbps, and it can come to the low bitrate, or it can exceed to the maximum bitrate as well. And then we have constant encoding, which we enable with the use of buffer, giving the buffer rate as well, and giving some average bit rates to operate that codec and for the video streaming as well. In that specific work, I opt the methodology. And for example, we have the test analysis. I choose or come up with some encoding parameters, as I mentioned, like the constant bitrate mode. And then we give I come up with a suit or a ladder of bitrate, give input to that specific encoder, and then it helped me to find the significant parameter. The significant, I call it here, which helped me to transfer that to stream that video with losing a very minimum number of frames. And then I model it with a VMAP, and it gave me optimized values on each specific bit stream rate, and which gave me like yield the higher VMAP or the lower VMAP or the average VMAP. So I just come up with analysis, a bit later, and then I found optimal solution. So the video format, we use YUV RAW, which is lossless format. Then we encoded it, and it is full HD, high definition resolution. The frame rate I use is 24, and I use the FFmpeg solution encoder tool to encode basically the original video. And I use the CBR mode. The codec I tested until now, it is MPEG H264, AVC, and MPEG H265. And this is just like idea. I set up a preset faster, and we set a tune of film. Those are some basic level results which I included in the paper. And if you can see, it's a ladder, which I'm using now in my detail experiment as well. So we start with minimum bit rate, and then we achieve. I went through basically 10 Mbps, 12 Mbps, and then we see the behavior of that video, how it relate or correlate with VMAP, how it on a certain codec, under a certain codec condition, how it perform, or what are the average retention value, which yield like gave me the good quality of video with losing minimum number of frames. So if I see it here, I compare two codecs, and then I can see the variation between two specific codecs, how they perform if I use input like a specific bitrate. So you can see it here on 6 megabit per second. Yield me a maximum number of VMAP. It means the video quality was better than that. So, but this specific test case helped me to come up with a condition of lower quality of video and higher quality of video and average quality of video, which will help me in my future experiment, which I'm going to show now. So this is the next stage of my experiment. Basically, I come up with the bitcode bitrate ladder. So you can see here, I use I'm going to build a data set based on full high definition video sequences. and I encode it in a high resolution and low resolution. So you can see here, we have minimum resolution, a low resolution, and we have a high resolution, okay? And then I encoded it with the minimum bitrate and maximum bitrate, like for the maximum, for example, over here, we have full HD. So I use 2 bit stream for 2 video sequences, which is like 2350K PBS and 3000 kbps. And I do it in a variable bitrate mode, created a buffer as well. So this is one form. I use this looseless video sequences, which is the condition for that experiment. And then I use encoder MPEG AVC for this specific experiment as well. I use FFmpeg to downscale sequences, then to lower the video resolution. And then for the VMAP, again, I need to upscale and then calculated the video as well. And as I mentioned, I have this ladder, video ladder, the bitrate ladder. So we have the use case is to use the lower resolution and high resolution with the low bitrate and the higher bitrate. The next stage is what I done. I need to deploy that offline encoded streams to MPEG Dash. Before I transform it to MPEG Dash, I prepared MPD, media presentation description files. So I embed basically the various resolution into one specific file. And then it give me then I segment it in M4S form. We have different segment duration. I can use lower segment duration, which is 2, and then I can do 4, 6, 8, and they depend on the encoder deployment. And then it impact the stalling as well, and which impact the latency later on. And I use GPEG MP4 box tool to transform it to M4S. In next stage, I deployed streaming server, which is Apache HTTP server. And that is deployed it in client and server configuration. I transform all the encoded video into the M4S segments, an MPD file into the server, which and I access it through different, FFmpeg command. Those encoded bits, video sequences, I then deployed a test bit, which is based on Dash, which name is Dash.js. It is an open source media player, which help us to stream that videos. And then we can perform different analysis. I recently created different cases, and one video sequences in a lower resolution, high resolution, how it will perform, what sort of buffer it will, utilize, and what kind of different, the test case, what kind of different use cases we can deploy under different network conditions. If we lower the bandwidth or if we higher the bandwidth, how it performs. So those are certain parameter or metrics which I'm using. And then from this experiment, it will help me to calculate the maximum number of stalls and like the volume of stalls and how that impact broadly on latency then. How those stalls will impact the quality of experience and latency itself. This is the overall scenario of that experiment. I will conclude it here. For this experiment, I'm going to do comparison based on different codecs, which is better performance codec or which codec perform in a specific case and specific bitrate, specific constant bitrate or variable bitrate with buffer, without buffer, how it perform. Then we can make some encoding decisions, which is specifically useful in this kind of experiment. And correlating it with different objective models PSNR or VMAP, that how it perform, how it vary from one codec to another. And then summing up all those, I can found the trade-off between latency and quality of experience, which is what are the amplitude of quality switching and how does it impact on quality of experience overall. That's all. It was a short presentation, and I will welcome if you have any suggestion, feedback. So I will welcome that. Thank you. Thank you so much.
Thank you. Very interesting. Please raise your hand if you have a question. I have one question to start with. Your range of resolutions goes fairly low, and I'd be interested in hearing from people in industry what they think of that range of resolutions. How likely are they to be seen nowadays? Maybe somebody from Meta might have, and oh, Yanis, I see your hand raised.
Yes, thank you, Margaret, and thank you, Said. Before I go into that, let me answer first of all your question. Yeah, this ladder that you present here, Said, is what we call a static ladder or a dynamic ladder. In other words, do you do something, customize these numbers for content, or is it just fixed, the same one for every content?
Okay, so my idea is basically I'm trying to find out the low latency systems, what kind of resolution and how does it affect on latency. If I make like the amplitude of styling, how does it affect if the timing of video, what it called this files. Encoded streams, how does it affect on the latency? It enhance increase latency or it decrease latency, and how much? So that was the main agenda or main thought behind it.
Okay, I somehow missed completely the latency concept. Maybe because of travel, my mind is still like spinning, but I missed completely the latency part. And is the latency induced because of processing? Because if you run a more sophisticated encoder in software, a system usually takes more time. Or is it, how is the latency controlled? Because of the low or
my
load?
thought, yes, my thought is when it is stalled, like for example, this chunks, next, we call it, okay, the segments, chunks, like if I encode it with the lower, you say like 2 seconds, and the video stalls. So that stall, how does it impact, the longer stall, the lower stall, the amplitude of stall, how much, like, and the what position of video, if it increase, and how does it affect overall in the latency? That is the thought,
And how did you evaluate it? Did you do subjective tests? Did you run any metric?
No, not really, sir. But this test bed, as I mentioned, the test.js, it give us some, we have some algorithm. If I name it, the low latency algorithm, which is already deployed. It just learned to adopt low latency, L2 LLL.
What algorithm? I mean, because you talked about evaluating the quality and the effect of stalling, right? Did you use any objective metric?
Yes.
That says this type of latency means so much quality. Did you? So you didn't do subjective testing, right? That's
no, not
okay.
really. I just prepared the video data set. Yes.
Okay, maybe I want to leave others. I see both Theo and Francois, who maybe are more lucid than me, but I still fail to see. But to your point, Margaret, it's extremely rare nowadays to see 235 kbps and especially 240p. I mean, it's not like it doesn't happen, but imagine someone who would be connected on a probably not even LTE, maybe high-end 3GPP. I don't know what's between 3G and LTE nowadays, but yeah, I would say 235 and 240p is something that probably nowadays is not in use. But again, thank you, Syed. I'll leave others maybe ask better questions.
Thanks. Thanks.
And perhaps Theo, I saw your hand maybe first you lined up. And apologies if I jump to moderate, but I think Margaret, either you are muted or someone else is talking.
Sorry, I was muted. Thank you, Yanis, for answering that question. And my thought set is maybe consider dropping those lowest bit rates or analyzing them separately. And then let's hear from Theo and then Francois. Theo? Theo, you had a question? We're not hearing you.
Yeah, sorry, can you hear me now?
Yes.
Oh, sorry. So I was saying that I appreciate the presentation from Syed. I just wanted to briefly comment on the trade-off between low latency and streaming QoE, in particular on the setup you have on slide 11. And my comment primarily is that, first of all, if you want to evaluate low latency, you may want to consider much smaller segments, or even, consider different application protocols such as CMOF instead of using. And the other thing is that I like that you use the Dash.js. I think that's a valuable or a reasonable direction. But just my comment would be that any latency and any QoE you evaluate will be a function of the adaptation algorithm. And so you have to take multiple adaptation algorithms into account and see how you can separate, the effect of the adaptation decision on whatever stalling on or latency you consider. And also, you have to set up the target latency and consider multiple values therein.
Yes, yes. Thanks, sir.
Okay, thank you. And Francois?
Maybe to your question, I guess, Margaret, on the resolution, I think you had a slide with all the resolutions you use. In the testing we've done, I've mostly done testing in United States. We don't see much of your first lower 3 resolutions in our testing, so they're perhaps on the very low side. So this is maybe just as an advice. We see more from your 5 to 8, and even sometimes also 1080. So I think your lower 2 or 3 resolutions are on the low side. That not sure that they're very popular. It also depends on the short form videos, the way they're encoded, and their popularity. Also, this is how we set up the resolutions. So typically, the more popular videos are encoded in very high resolutions, and after 30 days or 60 days, we're kind of downgrading them. But I haven't seen many of your first lower 3 resolutions. I mean, that's something for consideration.
Sure.
Thank you. And Yanis?
Yes, and before I forget it, I'm not sure exactly what was the aspect ratio of your video. If it was 16:9, row 1, actually basically most of the rows here, like 640x480, of course, 320x240, 720x480, they are not suited for 16:9. They are mostly for 4x3 or the older DVD standard. So I would say definitely this is an old slide that in terms of resolution misses a whole lot. So please check again. And if your videos were 16:9, you probably need a very different set of resolution. Thank you.
Thank you. Matthias?
Yeah, just a small clarification. If you go to the first part, this slide 8, 9, or 7 maybe. I think on 7. I think on 7 you say the you mentioned the codex, because I was wondering. You have
methodology.
Yes, so here you have H.264 and AVC mentioned, but those two are the same. Maybe you mean
okay. Yeah, it's advanced. Basically, it's MPEG AVC and HEVC, two different. Yeah, H.264. Yeah. So it's the format.
is
yes.
H.264 is the same as AVC. It's
correct.
AVC is the name of H.264.
Correct. Yeah. It's H.264 AVC. Yeah. MPEG H.264 AVC. Yeah. Correct.
And but then what is the third one? If you say you have 3. Or is it just 2 that you compare?
Yeah, I just put it here, like, but this is the preliminary work, and I carried out with MPEG, but now I'm interested to move on with other codec as well, considering other codec as well.
Okay. Yeah. Anyhow, then it's not important. Thank you.
Okay, Francois, did you have anything else to add? Your hand is still raised.
No, it's a stall hands. I'll lower that. Sorry.
Okay, thank you. Well, thank you very much for an interesting presentation. And I look forward to hearing more of your work as you progress. So, Matthias, so you're next, Matthias?
Okay, let me share my screen.
So I will turn off the recording now.
Yeah, thank you so much. Yeah, I'm a bit sorry about